Okay, this is the last video of the chapter, and we're going to look at some synthesis examples. So many of the reactions in this chapter are carbon-carbon bond forming reactions, and they yield products that have two functional groups. The reactions that fall into this category are the Aldol reaction or condensation, the Claisen condensation, and the Stork-Enamine synthesis. The Stork-Enamine synthesis just being a derivation of the microreaction, albeit oftentimes a more useful derivation of the microreaction because it allows us to do that reaction with a wider array of compounds. Now, which of these reactions we want to use, we can determine based on the position of the functional groups in the target compound. So in the Stork-Enamine synthesis, the product is a 1,5 dicarbonyl compound. So the two carbons that have the functional groups are 5 carbons away from each other. On the other hand, the Aldol and Claisen reactions have 1,3 difunctional compounds. So if we're doing a synthesis and we know we're forming carbon-carbon bonds, and we see that the two functional groups are 5 carbons away, then we're probably going to look to the Stork-Enamine synthesis, or potentially a more general microreaction. Or if we see that the two functional groups are 3 carbons away, then we are probably going to want to look to the Aldol and Claisen reactions. Now, another synthesis strategy that we can adopt from the reaction we learned in this chapter is putting alkyl groups on 2 adjacent carbon atoms. So we've learned 2 methods of alkylation. The alpha position of an enolate can attack an alkyl halide in an SN2 reaction, or in the microreaction, we can add an alkyl group to the beta position using a Gilman's reagent. And so we can also combine these reactions. And so if we first react our compound with the Gilman's reagent, we can put on the ethyl group in the beta position. If we don't follow this with acid, then we're going to have an enolate, and when I react that with the an alkyl halide, I can add that alkyl group into the alpha position. And so if you see, we're starting with an alpha-beta unsaturated carbonyl compound, and we've added 2 groups on adjacent carbons, then this is a strategy we're going to want to go to. Or even if we don't start with an alpha-beta unsaturated carbonyl compound, if we see that we've put on 2 alkyl groups, then I'm going to look and see, is there a way that I can make the alpha-beta unsaturated carbonyl compound, so then I can use this strategy to put on the 2 alkyl groups. So we'll finish up this video with a couple different examples. Alright, when I'm comparing my starting material to the final product, I see in the final product that I have 2 functional groups, and they're 1, 2, 3, 4, 5, where I have 1,5 difunctional groups. And so I immediately think of doing a Stork-Enamine synthesis. Now, the product of a Stork-Enamine synthesis, the 2 functional groups would be carbonyl compounds, but I know how to convert carbonyl compounds into alcohols. So I know I want to do Stork-Enamine synthesis, so before I even figure out what my Michael acceptor is going to be, the first thing I'm going to focus on is turning this compound into a carbonyl compound that I can then apply the Stork-Enamine synthesis to. So I've got to replace this bromine with a C double bond O. So I don't know how to do that directly, but if I could turn this into an alcohol, I could oxidize it. So if I want to turn that into an alcohol, because it's a secondary alkyl halide, I think I need to do that in 2 steps. So first I'm going to eliminate the bromine. And so I'll use a base that's not a nucleophile, so I don't have to worry about any competing SN2 reactions. Then, since the compound is symmetrical, I can just use hydration to put on OH, and then I can oxidize that. Since I have a secondary alcohol, any of my oxidizing agents should work. So now I've made my carbonyl compound, and so the next step is to do the Stork enamine synthesis. So the first thing I want to do is turn this into an enamine. So any secondary amine would work, so I'm going to use one with 2 methyl groups attached to the nitrogen. All right, now I can do the Michael addition. And so if I come back up and look, my Michael acceptor, so this is the carbon that's going to be forming the new carbon-carbon bond with a Michael acceptor. So this is the new carbon-carbon bond. So this is my Michael acceptor. So I want to react my enamine. I have 1, 2, 3, 4, 5, 6 carbons in the Michael acceptor. And then I need to put the double bond between the alpha and beta carbons. And then if I follow that up with H3O plus, I'll get that product. And then to get to the final product, I need to reduce it. And I can use lithium aluminum hydride to do that. And for the Stork enamine synthesis, I should have had the Michael acceptor and the acid in separate steps. All right, in this example, I'm starting with propane, and I want to make this compound. Obviously, my carbon skeleton has changed. I went from 3 carbon atoms to 1, 2, 3, 4, 5, 6 carbon atoms. And I have 2 functional groups, and the 2 functional groups are at the 1 and 3 positions. So this makes me think that for my carbon-carbon bond-forming reaction, I'm either going to want to go aldol or Claisen. Now, I don't have any esters in my product, and so I'm leaning towards an aldol condensation. And I can kind of see, right, if one of my aldehydes was that guy in red, and the other one is in blue, I can sort of see how the Aldol condensation is going to work. Right? This is the one that served as the enolate. So I had the enolate in the alpha position, and so this lone pair attacks the carbonyl carbon in the other aldehyde. Now, of course, in the product of the aldol condensation would be a carbonyl compound here and the alcohol here, but I know that I can reduce the carbonyl compound into an alcohol. So I need to do an aldol condensation. To do that, I need to turn this into an aldehyde. Now, it doesn't have any functional groups, so in order to functionalize it, we can do that. Now, that's going to put the bromine so that it is in the more substituted position. So I need to move that functional group over. Same way we did in the last example. Although now I need anti-Markovnikov addition. Okay, we need to oxidize this, but I have to be careful with the oxidizing agents I choose. I don't want to use sodium dichromate because that's going to take me all the way to the carboxylic acid. I want to get to the aldehyde. So these reagents should help me with that. All right, now I can do the aldol condensation. So we're imagining, right, this aldehyde was my enolate, so I had the lone pair here. That lone pair attacked the carbonyl group of, or the carbonyl carbon of the other aldehyde. Okay, and then the final step to get my product is I just need to reduce this aldehyde and lithium aluminum hydride will do the job. Okay, one last example. So now when I compare my starting material to the final product, I think one of the first things that jumps out at me is I've put two alkyl groups on, and they're on adjacent carbons. And conveniently, they started us with an alpha-beta unsaturated carbonyl compound. So we talked about how to do this. I want to combine Michael addition to put an alkyl group on the beta position, along with alkylation of the alpha position. After I do that, I need to do a functional group transformation. So I need to convert this aldehyde into an amide. But we know how to do that. So the first thing I want to do is put on my alkyl groups. And so I can do that with a combo Michael reaction. And so I'm going to do that with a Gilman's reagent. I want to put on an ethyl group. So that's how I chose my R group. Then if I don't do the water workup, I'll have an enolate, and then that can react with an alkyl halide. In this case, I want to put a methyl group on the alpha position. So that's going to give me a methyl group in the alpha position and the ethyl group in the beta position. All right, so now my task is to convert my aldehyde into an amide. So we want to get this into a carboxylic acid first. So sodium dichromate can do the job. All right, now I can't go directly from a carboxylic acid to the amide, but I can go through an acid halide. And then with this, I can react it with excess amine. In this case, I need methylamine. But that should give me the final product.